hardwired versus programmed logic. When we talk about something being hardwired, we mean that the way that it works, the logic that it uses, is a function of the way that wires connect things, or the way that they are electrically connected. So for example, when we have a start and a stop button that are wired to a relay to control a motor directly, then that's hardwired. There's nothing in between the input device, the start and stop button, and the output device. And the only way to change the way this works is by rewiring things. On the other hand, in programmable control, all the inputs go into a programmable logic controller, all the outputs come out from it, and the way that they're connected between can be changed in programming. And so if you want the stop button to mean go real fast, in the machine, you can make that happen. You just have to change the program. In PLCs, the most common way that inputs are converted to outputs is through ladder logic, where you have instructions, branches, the power rail, and rungs, where each rung takes some inputs and determines what an output on the right hand side should be. There are many different ways to create logic. One way is with a ladder logic program, but gates can also be used to make logic. So logic gates and or and not functions on little semiconductor chips can also make logic functions. So the relay schematic would be limit switch 1 and limit switch 2 have to both be on to turn on the solenoid. The ladder logic program would be input A, which is connected to limit switch 1, input B, which is connected to limit switch 2, are ANDed together in the ladder logic program such that the output Y, which would be connected to the solenoid, comes on. We can make this same expression with gates, where we have input A and input B going into an AND gate where both of them have to be on for the output to be on. But there's another way we can express that, and that is with a Boolean equation. And the Boolean equation says A and B equals Y. It may look like A multiplied by B equals Y, but what we really do is borrow the multiplication symbol to indicate the AND function rather than multiplication. Connecting two switches in parallel could be thought of as an OR function, because if limit switch 1 is on or limit switch 2 is on, then power will get to the solenoid and the solenoid will turn on. We can write a ladder logic program to do the same thing using A or B to turn on Y, and of course we can accomplish the same end with an OR gate, where we have limit switch 1 coming in on A, limit switch 2 coming in on B, and if either one is on, then the output Y will be on. Now the Boolean equation for this, to write it in a mathematical form like we're used to, would be A or B equals Y. Notice I didn't say A plus B equals Y. What we're doing is recycling the plus symbol. So plus no longer means addition, it means OR in this context. Now we can wire these up any way we like. We can have series and parallel logic functions. So you notice we've got limit switch 1, limit switch 2. If either one of those is on and the pressure switch is on, then the lamp comes on in our relay schematic. We can do that in a ladder logic program. A just has to be connected or reference limit switch 1, B has to be connected to limit switch 2, and C would be connected to the pressure switch, so that the output Y is on only if A or B and C is true. And you notice, let's jump down to the equation. I said that in the same way that the equation says it. In parentheses, we have to take A or B and the result was C, and the output is Y. In logic gate format, we take A or B together. That gives us the signal A or B. That signal gets ANDed with input C to produce output signal Y. So the pressure switch absolutely has to be on for the pilot light to be on, but either limit switch 1 or limit switch 2 can be on. Here's another logic setup that we could make, where we've got limit switch 1 or limit switch 2 ANDed with float switch 1 or float switch 2. And we can set up our ladder logic program to look just like the relay schematic. Our gate logic needs a little bit of thought though, because notice the intermediate point, the section between A, B, C, D, that vertical line there really represents the result of A or B. But then, whatever that result is, it gets ANDed with the result from C or D. So you see our gate setup has two OR gates running in parallel, whereas in reality the OR is in series, right? The A or B is ANDed with C or D. So that AND gate on the right represents the fact that A, B is ANDed with C, D. I should say A or B is ANDed with C or D to produce the output Y. In our Boolean equation, A gets ORed with B first, and the result is ANDed with the result of C or D to produce Y. But what does this program do? I mean, it seems interesting, but what is this doing? Well, what it's really saying is that if limit switch 1 or limit switches 2 is on, and if float switch 1 or float switch 2 is on, then the pilot light will be on. So we have to have at least one limit switch on and at least one float switch to be on for the pilot light to come on. Here's another setup where two limit switches are in series, in other words, ANDed with one another, and they are in parallel with a third switch. So we've got an alarm horn here. If limit switch 3 is on, I guess something really bad has happened. It's time to turn on the alarm horn. If limit switch 1 is on or limit switch 2 is on, things aren't so bad. But if limit switch 1 and limit switch 2 are made, then again the horn needs to come on and sound a warning. So you see the relay schematic, you see the ladder logic program that's set up the same way, where A references LS1, B LS2, and C LS3, and the horn is output Y. The Boolean equation is A and B. You see that together, that's taken first, and the result is ORed with C to generate the output Y. And you can see the gate logic as well, where we have A ANDed with B. That result is put into an OR gate with C to determine the output Y. Here we've got two series connected in parallel with one another to control a pilot light. So limit switch 1 and limit switch 2 have to be on, or limit switch 3 and limit switch 4 have to be on for the output pilot light to be on. You can see the ladder logic program reflects the relay schematic. You can see that the gate logic is the same as well, because we've got A ANDed with B, that result going into an OR and can drive the output, or C ANDed with D going into that same OR gate. So the Boolean equation is A and B or C and D produces the output Y. What about if we have a normally closed push button, for example, in series with a normally open limit switch? What would happen then? Well, obviously, if the limit switch is activated and the push button is not activated, then the solenoid will come on. And the ladder logic program illustrates this. It says if A is true and B is not true, then turn the output on. Now this is a little bit confusing. Let's finish this off, but then let me explain what's wrong with this. So the Boolean equation is A and not B equals Y. The gate version of this, we got to take B, invert it, and tie that in with A to an AND gate, and the output Y is then calculated. The only problem here is that if you were trying to wire up an equivalent ladder logic program to this relay schematic, remember that the push button would be naturally passing power. In other words, when it's inactivated, it would actually turn the memory address on, just like the limit switch has to be activated to turn the limit switch on. So in a real program with a normally closed push button, you would not use the B symbol with the slash through it, the inversion, because the natural state of the push button is that it is passing power. So I rather think about switches as either passing power or not passing power. But for the sake of understanding this, a normally closed push button is a lot like an inverted set of contacts. Now, remember that a normally closed switch does not require that symbol with the slash through it. You can use that one, you can use the other one. It doesn't matter. It depends on what your program calls for and what you need. Just remember that the push button that we've got here by default passes power. And so if we want our logic to be that the push button is not pressed and the limit switch is pressed before the solenoid comes on, we'd actually use the same type of contacts or the same type of instruction for B as is being used for A. Here's an example of an exclusive OR function, and this is a lot like three-way switches on your walls. You know how You've got, if you need to control a light from two different locations, you've got three-way switches on both sides, say, of a room. And you can turn the light on or off on one side, and you can turn it on or off on the other. If you think about what that really means, what that means is that, let's see, switch A, if switch A is on and switch B is off, then the output can be on. As soon as you turn switch B on, then the light goes off, right? On the other hand, if you leave switch B off and you turn switch A off, then the light goes off as well. So the setup looks like it looks a little more complicated than what we've seen so far. You see switch A is passing power through the lower branch, but switch B is not. Switch B has to be pushed down to pass power in this relay schematic, whereas if you push switch A down, power will pass through the upper portion of the rung. But think about the switches as either being on or off, and this will make sense. If A is on and B is off, then the output should come on. Think the lights in the room should come on. What does that mean? Well, that means that if A was on and B was off, the lights are on. But if we turn A off, the lights don't come on, right? They're off. On the other hand, since A is on, if B is turned on, the lights go off as well. So both A and B have control over turning the lights off. On the other hand, if A is already off, then when B is on, the lights will come on. But when B shuts off, the lights go off. Similarly, if A is off and B is on and A is turned on, then the lights go off as well. The gate logic setup is interesting because you need both the A signal and the inverse of A. You need the B signal and the inverse of B. And so we've got A going into an inverter circuit that then goes into an AND gate with B. That represents the lower rung, actually. And then we've got B going into the upper AND gate, okay, and then being inverted and going into the lower AND gate. So the lower AND gate is A and not B. That's actually the upper rung in the ladder program. The result of both of those two are ORed together to determine the output. So this is an exclusive OR function. Basically, when A and B are at the same state, both on, the light is off. When they are in the same state off, the light is also off. It's only when they are in opposite states, A on, B off, or the other way around, that the output, the light, comes on. Here we have a setup where two different start buttons can start the motor, but two different stop buttons can stop the motor. Notice that C and D are stop buttons that are normally closed, and this time the ladder logic is set up properly because C and D naturally pass power. But A and B are normally open. The motor will only start when either A or B is pressed, because the motor coils don't come on, the motor switch doesn't come on until the motor coil gets power. So C and D have to not be pressed for power to get through at all. Therefore, if the motor is running and obviously has sealed in, then breaking the circuit with switch C or switch D will cause the motor to shut off. So the logic is C and D, and the quantity of A or B or motor contacts gives you the output. I don't have the Boolean expression on this particular slide. So you can see how it's set up, where we've got a tri-input OR gate so that the output can feed back to the input. We've got switch A as one of the inputs to the OR gate, switch B as one of the inputs, and if any one of those signals is true, then the output from that first OR gate is true, the result of which goes into a tri-input AND gate. Basically, the stop button, either one, C or D, can be pressed to give a 0 in, and the AND gate is no more complicated than the two-input AND gate. Basically, the only time when you get a true out of this AND gate is when all three inputs are true. So the signal from the OR gate and the signal from stop button C and the signal from stop button D, have to all be true for M, the output of the AND gate, to be true. But if M is true, then the OR gate is satisfied, or if A is pressed or if B is pressed, then the OR gate will pass a 1 on and apparently turn on the motor. Now, with all this discussion of relay logic, PLCs, and now gates, you might wonder, why are we talking about so many different ways of making logic happen or doing logic? when PLCs are mainly what are used in industry. Well, a PLC is a relatively expensive device. If you say you want to design a washing machine, for example, well, washing machines have several different recipes. Like there's the delicate cycle, there's the heavy soil cycle. There's all these different cycles that have to be activated, and each one of them have inputs and outputs. For example, the tub has to be filled. If you're thinking of a vertical machine, the tub has to be filled to a certain level, whether you've got the switch set on high, medium, or low, before the recipe can continue. So that is input and output, and basically has to operate as a program. Now, older washing machines use a mechanical program type of system, but you could do these functions with gate logic. You wouldn't want to strap a PLC on the side of the washing machine and then try to sell it at Home Depot or Lowe's, because it would just be too expensive. The input logic, the brain, would just cost too much. It's too flexible. You don't need that kind of ability with the washing machine. It doesn't mean that you could then discover some better program and change it and have a super washing machine. It just means you've got too expensive of a logic device on the machine. So what you can do is use chips and programmable logic devices and things that use the same ideas of and, or, and not in logic in order to make decisions and control a process, but it could be a whole lot cheaper because programmable logic devices are relatively inexpensive. You might also even switch to a microcontroller, but these basic ideas of and, or, and not to make logic and make decisions and control machines is common throughout. In fact, we can represent these with Boolean equations, and those Boolean equations can be expressed as ladder logic or relay logic or even gate logic.